Okay, ready to check your answer. It look like this. So I changed this to phenyl just to make it shorter. Leaving group's gone. You have to look at the substrate, find your leaving group. Never a carbon group or hydrogen. Must be the iodide. It's gone now. Look over the arrow, find your nucleophile. Not the strongest nucleophile, but it doesn't matter. We're in SN1. SN1 can have a weak nucleophile. So this is moderate to weak nucleophile. It's stronger nucleophile than something neutral, but it's resonance stabilized anion. It's not particularly strong, right? Now, DMF, that's a polar aprotic solvent. Remember solvent, we wanted to be protic, but oh well, it's not a deal breaker. What really matters is the substrate, the nucleophile. So you might say, why can't this do an SN2? Let's look at the substrate and just check. 1 carbon group attached, 2 carbon groups attached, so it's secondary. So the reality is, an SN2 could work. If you really wanted to favor an SN2, you would need a very strong nucleophile, like it's not resonance stabilized. But because we didn't do that, and secondary will actually allow for SN1 to happen, and probably at a greater degree, we're going to probably take that path. But as you can see, they can overlap. You got to make a judgment call. So in this case, I'm saying draw the SN1 products. So let's show that, because that's what this section is. Leaving group leaves. Then we have our carbocation. And I'm not gonna draw it in and out of the plane anymore. I'm just gonna draw it flat in the plane of the paper, the page. There's our carbocation. Here comes our nucleophile. O, this acetate group with everything on it. The whole shebang, not just the O, goes on there. Everything attached to it. So this attacks from either side, above or below the plane, which means we're gonna get this whole group, this is our new group, on a set of enantiomers because we have a stereocenter, right? So we get racemic mixture. So those are the products. So something just to remember, SN1 products produce, or SN1 reactions produce a racemic mixture if there's only one stereocenter, assuming there's one stereocenter, which is most of the cases. But if, like I said, if there's a pre-existing stereocenter, then it's semantics. We're trying to decide, we really still made the opposite. We made both of the opposites, but the pre-existing stereocenter that's also there makes that relationship now diastereomers. Lots of practice to do clearly, because this one will not encapsulate all scenarios or all ways to draw it. Like for example, the leaving group's in the plane here. You want to do so much practice that you're comfortable. What if the leaving group is on a wedge? What if the leaving group is on a dash? What if it's on the plane this way? What if it's flipped around? What if it's in a big molecule? What if it's in a small molecule? What if it's not this leaving group? Practice, practice, practice. There is some practice problems here. Let's summarize this real quick. Sometimes, like I said, we have to make a decision. If we say, okay, I know I have a nucleophile, I know I have a leaving group, but it's secondary. Oh no, how do I know? How do I know which way it's going to go? So we're going to pick which one would dominate, okay? And what helps it dominate always comes down to the most stable transition state. Okay, so let's encapsulate both substitution reactions. Both reactions, when it comes to leaving groups, require a moderate or better leaving group. So that will not help us decide. We can't look at the leaving group and say, aha, it's SN1 or SN2. They both require moderate or better leaving groups. How about the substrate? Ooh, this helps a lot. If it's tertiary, it can only be SN1. SN2s don't work in tertiary. No space, it's sterically hindered. No backside attack. If it's primary, without resonance, or methyl, it can't be SN1 because that's a horrible carbocation. It can only be SN2. So those two extremes are sorted. You see that kind of substrate, we're set. The hard decision comes when it's in the middle. Is it secondary or primary with resonance? Then it could be both. So let's go down and evaluate other factors. That means look at the other factors if that's the case. Nucleophile. If it's a very strong nucleophile, usually a full-on negative charge, we're going to go SN2. Why? Think about the mechanism. The substrate, in order to do an SN1, the leaving group has to leave. And then usually that only happens on its own because the nucleophile is too slow to get to it. If you have a really reactive, strong nucleophile, it's not going to wait for the leaving group to leave. It's just going to go ahead and attack if it's possible. So that's why we're talking about these scenarios where it could be SN1 or SN2. If you're trying to decide, look at the nucleophile. If it's strong, you're doing SN2. If it's weak, often that means a neutral charge, like alcohol or water. That's the most popular. ROH or H2O. It's not going to do SN2. It's too slow. I'm guessing one. So the nucleophile is a good tell also. Solvents, once again, if you get to have your choice of how to speed up a reaction or promote one reaction over the other, then you can pick the ideal solvent as follows. So SN2 reactions actually do prefer polar solvents, but will work in nonpolar. But SN1 require, they will not work in nonpolar solvents. So if you see a solvent that's not polar, you can't do an SN1. It's because that carbocation is just too hard to form. You need to have everything going in its favor to make that happen. SN2 reactions prefer aprotic solvents, but SN1 prefer protic. But the key word being prefer, meaning that's not a deal breaker if it's not. Okay, so there's a lot of practice problems here and some more that we'll see together, but I want you to give these a try, okay? Like I said, here's some kind of obvious starting points that are a little more simple. We'll start off simple where we have the leaving groups. This is the same substrate. Two different things over the arrow. Look at that nucleophile. Strong nucleophile, weak nucleophile. So I take that back, I lied. I'm going to do this one with you, these two with you. That'll set you up to try some challenging ones. But I want you, it's still worth pausing and coming back to try it because that helps a lot. But I just feel like we should do a little more. Okay, so let's go with comparing these two. What are we doing here? The exact same substrate. So carbon has two carbons attached. There's our leaving group, right? So you identify your leaving group. Here's my leaving group. Identify your carbon on the leaving group as primary, secondary, tertiary. The carbon with the bromine attached has two carbons attached, so that's secondary. Look over the arrow. Solvents, not really specifically overtly stated unless it's actually also water, in which case it could be salicylic. This is but we have to find our nucleophile. So this is our nucleophile. Here's our nucleophile. Which one's stronger? Clearly the hydroxide, right? Water is actually considered a weak nucleophile. That's the only difference here. What's over the arrow? And sometimes that's all you need to see. Strong nucleophile means SN2, provided the substrate will allow it. Weak nucleophile means SN1. All right, so SN2, we know how to draw that. Backside attack. Let's do that first, get that out of the way. Put there and leave. Only one product. Bromine on a dash. Oh, what am I doing, bromine? Bromine's gone. OH on a dash. I think I'm getting tired. We'll pause after this one and let you guys do the practice problems. Okay, so only product. There we go. All right, what happens with SN1? Well, the mechanism says leaving group leaves. Now I have a secondary carbocation. I should think about rearranging, but no matter what I do, it's not going to get better than secondary, so I'm going to keep going. Prove that to yourself. Time to capture a nucleophile because we already decided on SN1. Water attacks. Water attacks using its oxygen, and everything stays attached to it. You don't just break water apart. See that sometimes? And I don't know why, but we are not going to let that happen. Water attacks the oxygen and its whole being. Embrace all of water. It's there. You can't break it off like that. But it is positively charged. This is called an oxonium ion. Notice I lost my dash and wedge, right? Because I have both. I have that one. So sometimes we'll lose it and we'll actually just state that both are there, but not yet. We're not advanced enough with that yet. Okay, we made an oxonium ion. It's like a hydronium ion, only with an R group, like H3O plus, right? What do we do to H3O pluses? We use it as an acid. We deprotonate it. We neutralize it to water. What do we do with oxonium ions? We deprotonate them, neutralize them to alcohols. Who can do that? Who was our nucleophile? It's also going to be our base. So thank you, water. So HOH, more water comes along and neutralizes. Let's do it again over here. HOH. There we go, our nice, clean, finished looking products. OH, new group on a wedge, plus OH on a dash. Box it up like a present and compare. SN2, very typical. SN2, only one specific stereocenter. SN1 products, racemic mixture. Both substitution replaced the leaving group with a new group. Bromine's gone, but now it's inverted, just like in SN2. Bromine's gone, but we have the representation of it replaced on a wedge, also replaced on a dash. Okay? All right, so these are a lot of fun. It's ramping it up. Maybe return to it after doing some studying, some nice ring-forming ones. We'll do these together, okay? Give it a try. And as you can see, it says draw the mechanism. You can see that the product's given. So it's not draw the product, it's draw all the arrows. So that's typical of a mechanism problem. Arrows are missing. How did this become this? Show those steps. At least show what you can. If you don't get every part, that's still better than coming back with nothing. Okay, and then work your way down to this one. We'll do all of those together, but I want you to try to show the arrows to explain all of that, okay? Show the steps. So in other words, one way you could practice for the next one is to redraw this, but the arrow's missing, and you fill in the arrows, right? So that's the mechanism. All right, practice, practice. Mechanisms are the key to understanding the products. Don't skip that step. Mechanisms are crucial. So I want you to take some time on that rather than watching me do it, and we'll do it together when we convene again. Bye for now.